Hello, so in this video we will study about the weak acid base and strong base or acid titration. So first we will start weak acid and strong base titration, and there are some important point to note down. That number 1, the weaker the acid, the smaller the Ka. So we have seen already that if Ka value is less than 1 or very small, basically dissociation will be very small. So it means acid will not dissociate into hydrogen ion and anion. So if Ka is very small, then it means acid will be the weak. Number 2, the weaker the acid, the higher the initial pH. Weaker the acid means pH will be higher, means it would be towards more neutral side, right? So if the pH is 1 2, and this will be very strong acid, and as we are moving toward the neutral pH around 7, so here, so pH is going to be higher, right? So if you see that pH is going to be higher, this is the pH on the left hand side on this graph. So pH is around 6 or 4 or 5, so that is called the weaker acid. The weaker the acid, the smaller the rise near the equivalent point. So here you can see equivalent points are in this region. If the strong acid, which is have 1 or 2 pH, and if you see these two line, the black line and red line, their equivalence points are very near to the 7 and as we are going to the weaker acid, their equivalence points are rising slowly toward the basic pH, right? So at equivalence point pH will be more than 7, so we can say these equivalence point 1 2 3, at least 3 of them, they are pH is more than 7 for equivalence point. So the pH at equivalence point marked with the circle increase as Ka decreases. So we can say that pH and the relationship between the Ka and pH is inversely proportional, right? So if pH is higher, Ka is very small. Next is the weaker the acid, the higher the pH at the equivalence point. So we have already studied. So these are the very important points we have to keep in mind when we are studying the strong weak acid and strong base titration. So next is how we can understand, or how we are going to keep the record the pH for weak acid and strong base titration. So look at this graph where we are going to do titration of acetic acid. This is the weak acid, and we are going to, so this is the weak acid, acetic acid, and NaOH is sodium hydroxide, is a strong base, right? So this is the titration between the weak acid and strong base, and we are going to generate sodium acetate, this is salt and water. So equilibrium lies between the acetic acid and acetate with water. So this titration is start from here, which is pH is around 2.5 or very close to the 3, and then we have somewhere a midpoint which is here, right? Somewhere here, this is the middle point, and when we reach to the equivalent point, and equivalent point is above 8, so you can see pH is above 8, even above 7, basically neutral. So the equivalence point is lies in the basic region, and at the end we are going to the basic condition. So if we look at this graph, so y axis is increasing order of the pH, and x axis from left to right we are increasing volume of ml of NaOH base. And what are these bubble says that equivalent point occur when mole base is equal to mole acid, right? So this says at the 50% or 50, what is the meaning of 50 ml, or what is the meaning of equivalence points? And then at equivalent point it says that the pH is more than 7 at equivalence point because acetate ion is a weak base, right? And the third bubble says that pH changes near the equivalence point is smaller than in strong acid and strong base titration. So let's understand this graph to how to calculate the pH at different level. So if we are in a case of A, this is the A case, this is the B case, this is the C part, and this is the D part. Let's segregate the whole graph into the A, B, C, D. So we are going to start from here A. So in case of A, we have only acetic acid, and acetic acid is a weak acid. So we will write like HA for the weak acid. And if you remember how we calculate the pH for the weak acid will ionize into hydrogen ion and anion, and we calculate their pH based on the ice chart, ICE, right? We will make ice chart, and then either, so pH of this case, in this case, will be either ice chart you can use, or we can use Henderson-Hasselbalch equation, HH equation I am writing here, which is Henderson-Hasselbalch equation. So but mostly preferable is this one, right? So I will say at this condition we are not going to use Henderson-Hasselbalch. This is one choice, but it would be because there is no salt, so we cannot use this Henderson-Hasselbalch equation here. Henderson-Hasselbalch equation we can use at the B condition. So let's see what is going on in the B. So we have only acetic acid here, and pH we are going to calculate based on only ice chart. Once we will find out the hydrogen ion concentration, we can take a negative log of the hydrogen ion concentration, and that will give us the pH. Next is the B condition, where we started adding the sodium hydroxide. So once we are going to add sodium hydroxide, we are started generating the sodium acetate, so there will be some salt will also be started. So basically at this point we are going to use, at the B condition, we are going to use pH by, here we will use Henderson-Hasselbalch equation, pH by Henderson-Hasselbalch equation, because this is a kind of buffer region, right? This is a buffer region, and also why it will be like this one, because here we have acetic acid CH3COOH, which is in excess amount here, and then we have some salt. So weak acid and salt, the combination of these two will allow us to calculate the pH using Henderson-Hasselbalch equation. So these are the three things will be there. And here is very important thing, once we will reach to the half point of the buffer before equivalence point, this is the half point. So at the half point of the B what will be happen here? So let me show you here in this. At the half point of the B, halfway point, basically we are going to add only half mole of titrant, means NaOH titrant, and at this condition titrant is here NaOH, right? And at this condition pH will be calculated based, will be actually equal to the pKa. So half point, pH will be pKa. In the buffer region, Henderson-Hasselbalch equation, and at A point, ice chart. Let's talk about the equivalence point, the C point. So C point, what we have here? We have only sodium acetate, CS3COO, and then plus water, and sodium acetate will 100% dissociate. It will form sodium ion plus acetate ion, CS3COO minus, and acetate ion will react with the water to form acetic acid plus OH ion minus. So what we will do here, we will use ice chart. We will use ice chart to find out the concentration of OH. Once we will know the concentration of OH, and then we can calculate the, and using Kb, because here we are using, this is the base, and then we can take the POH of this one. Once we will get the POH, we will subtract from 14 minus POH to get the pH. So this is the way at third or at equivalent point we have to calculate the pH. Let's talk about the last part, where no acid left with excess of NaOH. Here only NaOH will be there, so we have to calculate how much NaOH concentration will be there, right? So basically we have to calculate excess of NaOH, right? So, and also here I would like to show you that A to B region, this is the this region A to B. Let's assign these region also. Sorry, this is the B region, buffer region is B, this is the C region, and this is the D region, right? So A to B region and B to C region, B to C, they are in the buffer. This is called buffer region. And pH is calculated by Henderson-Hasselbalch equation, which we have already explained here. So, and at this point, D point, we have to find out how much excess of NaOH will be there. Once we know excess of NaOH, we can calculate the negative log of hydroxyl ion concentration. We will get the negative log of hydroxyl ion concentration to get the POH. Once we will know POH, we can subtract from 14 to get pH. So these are the flow chart we have to use to understand the weak acid and strong base titration and problem solving strategy. First, determine number of moles of acid and bases. Determine at what step of the titration you are at, whether A, B, C, D. Weak acid or weak base only means this is like a part, we are here A. Use ice chart to find out the pH of weak acid or weak base. So this is reverse also possible. I mean, you can use a weak base and strong acid, so it will apply, these strategy will apply on both of them. Equivalence point, before equivalent point, basically they are talking about A to C, or I will say that A to B, or A to B, or B to C, right? So check if half point, you are at half point. If you are at half point, means moles of strong base or acid will be equal to half mole of weak acid and base, and then at that time pH will be equivalent to pKa. If not, then you are in the buffer region, in buffer range. Use neutralization equation to find the number of moles of weak acid bases remaining as well as those conjugate salts formed. Then use Henderson-Hasselbalch equation. At equivalence point means we are at C point. At equivalent point, all that is present is the salt. So find the pH of the solution, ice chart of the hydrolysis equation with the new volume. And the D part, past equivalence point, calculate the excess mole of a strong acid or strong base to determine the pH from the hydrogen ion concentration or hydroxyl ion concentration. So these are the some strategy we have to use to calculate the pH at different stages in the weak acid and strong base or weak base with strong acid. And in the next video we will try to solve two examples related to this topic.